So today we're going to start looking at the second law of thermodynamics. Oh, some questions anyway from the second law of thermodynamics. So we'll start with question 6.2. Your refrigerator extracts 2.5 kilojoules of energy from the food in the cabinet. If its compressor requires 1.5 kilojoules as an input, determine the coefficient of performance of the refrigerator and the amount of heat rejected into the room. Okay, so let's just go over quickly what a refrigerator is. So let's say we have a relatively warm region, we'll call it hot, and a relatively cold region. And we have a refrigerator between it. Never mind exactly what's going on inside, but we have some system in between these two. And what it's doing is it's taking heat from the cold and moving it over to the hot region. Okay, we'll just put R here because this is the refrigerator. Now, we know one of the statements of the second law of thermodynamics is that it's impossible to have a system that takes heat from cold and moves it to a hotter region without anything else happening, right? And that's actually the case. There's actually something else happening here, and it's that we're putting in work into the system. So this, we'll call it Q in because it's going into the refrigerator. We'll call this Q out because it's going out of the refrigerator, and this is work in. Now, the way we put in work is we power a compressor to run the system. All right. Now, the Q that's going into the refrigerator is the Q that's being taken away from the area that you want to keep cool. So we want to maximize the Q in. Work in is obviously costing us energy. We want to minimize that if possible. And Q out is the sum of the two because, of course, we have Q going in, work going in. So Q out being the only outlet of energy has to be the sum of Q in and work in. Okay, so of course, Q out is going to be bigger than Q in and work in individually. It's going to be the sum of both of them together. And that's the heat that's being rejected. And this is what you see at the back of a refrigerator where you have those sort of coils where you're rejecting heat from the sum of the Q in being the heat that's removed from the refrigerated area, and the work in, which is the work that's being input to the compressor. So this is how a refrigeration system, from a high level anyway, works. Now we're told that we're removing 2.5, I believe it was kilowatt, I can't remember the number. Sorry, kilojoules. Okay, so in some amount of time, we've removed 2.5 kilojoules from the area we want to keep cool, and this cost us 1.5 kilojoules of input energy to the compressor. So we want to find the coefficient of performance and the Q out. So the Q out is actually pretty simple. We'll start with that. Okay, we know since Q out has to be equal by the first law of thermodynamics to the work in and the Q in. Well, the Q out is going to be 1.5 plus 2.5. So the Q out is going to be 4 kilojoules. And again, it's bigger than the Q in. This is because it's not just the Q in that it has to reject eventually. It's the work input as well has to be rejected in the form of heat. Now, what you'll notice about this entire system is that it's the exact opposite of a heat engine. So if we look on the side at what a heat engine does is we have sort of the hot area and the cold area being the boiler and the condenser. And our goal is to output work by putting in heat from the hot area. And of course, by the second, we're going to have some amount of heat that's wasted to the cold area. And if you look at the directions of the Q in, Q out, work in, work out, you see it's at least relative to where it's coming from, the hot or the cold reservoir, it's the exact reverse of the refrigerator. And this makes perfect sense because when you look at it, they're really just one is doing the opposite of the other. So if a heat engine is made to produce work based on a temperature difference, a refrigerator uses work to create a temperature difference. So it makes sense that they work in the exact opposite way. Now, on to coefficient of performance. Well, coefficient of performance is the measure of efficiency of your refrigerator. So it's basically the parallel of thermal efficiency, but of course it doesn't work the same with a refrigerator. We need to find something called coefficient of performance. And for any type of efficiency, we really want to measure it in what we're getting out of it versus what we have to put in. Now, what's the goal of any refrigeration system? We want to pull out as much heat from the cold area as we can. We want to maximize our Q in. So Q in we want to maximize, and then we also we also want to minimize for given Q in. We want to put in as little work as we need to. So we want to put in the denominator work in. And what you'll notice is that, well, of course, 2.5 over 1.5, and that comes out to 1.6 repeating. You'll notice that the coefficient of performance is always greater than 1. And this is different from the thermal efficiency, which is always less than 1. But that's just how refrigeration systems work. The way we define their how good they are at doing what they do is coefficient of performance, and it's always greater than 1.